Hey everyone, this is James here. This is actually just a quick recording that I'm doing of a talk that I'm going to be giving soon at the Exercise Summit in Lisbon, Portugal. But I wanted to run through it quickly just to check the timings, the flow of the presentation, and so on, so I can make some edits to it before I actually give the talk in person. So I figured why not actually record it so that I can share with people and see if it's something that they find valuable and interesting. So I'm going to go ahead and make a start with the presentation, and I'll do so in a fairly raw, unedited format. Obviously the point of this is to try and see whether or not I can actually cram everything into the approximately 40 minutes that I've got for the presentation, and make any edits and cuts as necessary before I give the talk in person. So let's crack on, and hopefully this is of interest to people. I know it's a different sort of perspective than many people are used to in our field regarding approaching research and also practice. The title of this talk then is the value of strong theory in exercise science for both research and practice. And this is a topic that I've been very interested in for a number of years now, and have been trying to communicate more clearly to the broader field of sport and exercise science, and also been using very much so to try and guide my own research and the work I do in collaboration with others. A general outline for the talk then. On the wrong screen there we go. So I'm going to give a very brief introduction to philosophy of science. More specifically, I'm going to go through specifically the kind of framework that I use to, or my own kind of positionality with regards to philosophy of science, and how I use that to guide the work that I'm doing, to provide a bit of context for the examples that I'm going to give later in the presentation. I'm going to talk a little bit about what theory is and what I think makes it strong. I've spoken on this topic before, so for those of you who have seen my previous Stork talk, you might recognise some of the content from there, and I lean heavily on excellent work from the kind of cognitive and psychological sciences regarding theory development and testing there. And then I'm going to go through, as I say, examples from our own recent work regarding how we have worked to try and develop strong theories, and then use that to guide our research and conduct strong tests of those theories, before then hopefully providing some context as to why I think this is important also from a practical perspective. So why are all these kind of heavy going and potentially fairly boring topics for practitioners, why are they still important for helping guide their practice, and finish up with what I think are some hard truths for exercise science as a result of these. So, brief introduction then to the philosophy of science, or my philosophy of science at least. So I do want to quickly signpost to an open access preprint of a introductory book chapter that I've written for a co-edited textbook on research methods with Dr. Amir Dolan and lots of excellent contributors, which will hopefully be finished up by the end of the year and available. But in the meantime, the introductory chapter, which covers a lot of the content that I'm going to cover from a philosophy of science perspective, is covered in more detail there, albeit still at a very introductory level. So please do check that out if you're interested in learning a bit more about those topics. Okay, so why should you care about philosophy? Well, I'm going to start off with a quote, because I think this quote kind of emphasises my kind of views and perspectives on why philosophy is important to think about and use to guide the work that we're doing. So Albert Einstein, in his letter to Robert Thornton in 1944, wrote, "A knowledge of the historic and philosophical background gives that kind of independence from prejudices of his generation from which most scientists are suffering. This independence created by philosophical insight is, in my opinion, the mark of distinction between a mere artisan or specialist and a real seeker after truth." And that's always been the motivation, at least for me, in terms of wanting to learn more about philosophy in general, and specifically the philosophy of science, to really try and understand and guide the work that I'm doing, and really, as I say, emphasize that kind of real seeker after truth statement that Einstein says there, rather than just being a kind of artisan or specialist who's very good at very specific kind of technical things, but one who can think more broadly and more conceptually and more philosophically about the work that I conduct. Okay, so Peter Kors, in his classic book, textbook on the philosophy of science, breaks it down into 4 primary branches. We have ontology, the theory of being; epistemology, the theory of knowledge; axiology, the theory of values; and logic, the theory of inference. Now, ontology essentially refers to what we assume reality is, what we assume is there for us to potentially produce knowledge about. And epistemology refers to what we assume we can do in terms of our means of actually producing knowledge. Or axiology refers to primarily elements of morality or even ethics with regards to science, and logic refers to the specific forms of kind of argumentation and reasoning and inference that we can engage in. Now, I'm going to set axiology aside for the purpose of this talk, and I'm going to focus primarily on just giving you an overview, as I say, of my kind of ontological and epistemological perspective, and how I think the different kinds of key modes of reasoning or logic fit into a holistic view of science. So, let's start off then with ontology and epistemology very briefly. Now, I subscribe to, or I follow largely, Roy Bhaskar and Nancy Cartwright's kind of tripartite ontology. So, I am what would be called a realist. So, I assume that there is a independent reality that we can know about and we can produce knowledge about. But I'm also a fallibilist when it comes to what I think the knowledge that we can produce. So I'm not one of these people who thinks that we can produce objective knowledge. I think we try to produce knowledge that is as close to the truth that we assume to be out there as possible, but that we can always be wrong in the kinds of claims that we make regarding the makeup of reality that we think we're trying to know about. Now, there's a reason why there's a coffee cup here, because this is an example that I used to use with my undergraduates to try and kind of explain this to them. So, using Bhaskar's terminology, he splits his kind of ontology or his kind of stratification of the reality that we're interested in into 3 different realms: the empirical realm, the actual realm, and the causal realm. The empirical realm being the observations we can make, the actual things that we see out there, the data that we produce in the context of our research. The actual realm being the kinds of patterns and phenomena and events that we infer from those observations that we make. And the causal realm being where we think there are, or where the underlying powers or mechanisms or dispositions that lead to the phenomena and patterns that we infer from the observations that we particularly that we make out there in the empirical world. So, to use the coffee cup as an example to try and kind of make this make sense, let's say I'm holding on to my coffee cup and I let go, and I notice that it falls to the ground. Well, as I say, this is an empirical observation. It's what we would usually call data in our study. In fact, if we were to do it over and over again, then maybe we'd be more likely to call it data, given that there's lots of it. But if we did it over and over again, we might notice that every time we let go of the coffee cup, it falls to the ground. So there seems to be this kind of pattern, this phenomena, this kind of coffee cup falling effect that occurs when I let go of it. Now, we could draw the inference that there seems to be this constant conjunction of events that occurs. I let go of the coffee cup, it falls to the ground. There is a pattern here. There's a phenomena occurring. But we could be wrong about that. There could be, for all we know, next time we let go of the coffee cup, it could float upwards. So we could be wrong in the inferences that we make about this, but in general it seems as though there's some sort of pattern there. So we might then start to move on to asking, well, what explains this constant conjunction of events? Why does it happen? Why is it when I let go of my coffee cup it falls to the floor? It seems to consistently do that. Well, this is where we start to then come up with possible explanations for it. So, for example, the theory of universal gravitation, or the law of universal gravitation, explains why that seems to be the case, given the context in which we're doing it. So this underlying unobservable cause is something that we posit as an explanation, or we infer as an explanation for this pattern, which explains the observations that we make. But we can be wrong in all of these steps in terms of the inference that we make. So whilst we might claim that we have knowledge of a particular pattern and we have knowledge of why it might occur, we can be wrong in all of those steps. Now, let's just use an example then quickly from exercise science that might solidify a little bit more. So let's think about the context of responses to resistance training in terms of muscular hypertrophy. So in the empirical realm, we can make measurements of exercise performance or measurements of muscle size, and we might start to notice that people who take part in a resistance training intervention over time show consistent increases in muscle size of a particular magnitude or a particular form over time. We might see that there is particular patterns of changes that occur that we can infer from these measurements and observations that we're making. And then we might posit underlying causal mechanisms for why that might occur. So I think this is a really useful way of kind of stratifying and thinking ontologically about what it is that we're interested in. It also helps you think about what it is that we're doing with our studies and how we use them to test explanations, test the patterns that we're interested in, test the causal explanations that we come up with. So let's now very briefly move on to talk a bit about logic. So there are three key branches of logical inference or reasoning. There is deductive logic, inductive logic, and abductive logic. Now, deductive logic is the form that starts with a particular general statement or a premise or premises, and then moves towards a logically entailed conclusion. So, for example, if we start with the premise, all men are mortal, and the additional premise that Socrates is a man, well, therefore, it's logically entailed that Socrates is mortal. And he subsequently tested that idea by drinking the hemlock and subsequently perishing. So deductive arguments start with a general set of premises, and if they're a valid logical form, they will lead to a particular guaranteed conclusion. And particularly with regards to science, philosophy of science, Karl Popper, the philosopher of science, was famous for implementing a particular kind of deductive argument called modus tollens in his falsificationist scientific philosophy. So in this, he would start with something like, if my particular scientific theory were true, then we would observe particular things, or we may not observe particular things. We can then go out and say, well, let's make some observations, and they become another premise in our argument, and we either do or do not observe the things that our theory says we should observe. And so in the case of not observing the things that our theory says we should observe, well, we can logically reject our theory then, because the theory says if it were true, we would have to see a certain set of observations, and we don't see those, and so we can falsify our theory. And this is, albeit there is obviously fallibility in this when we bring it to bear in the empirical world, because there's still a lot of assumptions that go into our set of premises, logically the argument is guarantees the conclusions. Now, if we did, for example, observe the things that our theory said we should observe, well then what that implies is that the theory may have some degree of verisimilitude to it, or truth-likeness. It may corroborate our theory, but it doesn't guarantee the truth of that conclusion. And this is what inductive logic essentially follows. We start with a particular observation or set of observations, and from this we make broad generalizations. Or in essence, we make probabilistic inferences, not guaranteed inferences, from the observations that we make. So for example, let's say we've only ever observed white swans. Well, we might then infer that all swans are white. But that inference would only be probabilistic. It's not guaranteed based on the observations that we've made. All it would take is for one simple observation of a black swan, for example, to reject that. So inductive logic is often used with regards to kind of theory corroboration to some extent. If, for example, our theory passes a particular attempt at falsification, we might inductively infer that there's some increased probability of our theory being true. But it's more often than not used to infer particular patterns from observations that we make. So to make inferences about the actual realm from the empirical realm. Now, lastly, we have our abductive reasoning, and this is where we essentially start with some set of observations that we're interested in, and we come up with what we think might be the likeliest possible explanation for those explanations. So, for example, we might look outside and see that the grass is wet. But if it rained last night, then of course the grass would be wet. So therefore, there's some reason to suspect it might have rained last night. And this conclusion seems to be a reasonable explanation. And we could, for example, then take it forwards and make some deductive arguments about it and try to falsify it. But we can also come up with other candidate explanations as well. So, for example, someone might have just used the garden hose, or maybe it's dew condensed from the moisture in the air, and so on. So abductive inference is often used to come up with possible candidate explanations for the observations or the phenomena that we observe or that we infer, and then to bring them towards our deductive structures to make tests of them. And so, as I say, this kind of holistic view of how we use all of these different kinds of logical forms to draw inferences in the sciences fits quite nicely in this this figure that I've recreated here for and used in the textbook chapter. So, for example, we might make particular empirical observations and produce data from them, and we might try to, similarly, for example, with the observation of the lawn being wet, come up with abductively infer explanations for why that might be the case, thinking about the kind of causes that might have led to it. Normally more likely in the context of our science, because we typically make lots of observations and collate them as data, we might inductively draw a generalization about there being some particular phenomena here, some particular event that seems to occur constantly. And from that, we might come up with some causal explanation via abduction about why that might be the case. Once we've done that, though, we then start to have some theory that we can bring back to bear on the empirical world. We can, from this theory, make a deductive prediction. We can instantiate our theory as some sort of model. We can use that model to draw up some operationalization of a particular study design that we're interested in. And then we can go out and make those observations and test deductively whether our theory is falsified or not. If our theory is falsified, then great, we can start to come up with additional new possible explanations and we start the cycle again. Or if our theory passes the test, we might tentatively infer inductively that there's some degree of verisimilitude to it, some degree of probabilistic corroboration from that test that we've engaged in. Okay, so hopefully that gives you a good overview of my kind of approach to the philosophy of science and how I view kind of scientific inference, and it will then make more sense when we go through the examples shortly. But for now, let's touch on what theory is and what makes for a strong theory. And what I'm going to focus on primarily, given the topic of the talk is focused around the exercise sciences, is I'm going to focus on intervention effects, because more often than not in our field, it's the main thing that we're interested in. We're interested in what happens when we do a particular intervention. When we're exposed to a particular intervention, what is its effect on a particular outcome? So, borrowing another example from Amir, which I've used before, which is let's think of a intervention like stork juice. So let's say there's some sort of new supplement called stork juice, and when people take stork juice, we can make specific observations of what happens when they, for example, take placebo versus stork juice, and we can start to infer that there is some sort of stork juice effect here. There seems to be the phenomena that people consistently improve performance when they take stork juice. But it's not just, as I say, the effect that we're interested in. We're interested in explaining why the effect occurs. What is it that gives rise to the effect? What is the underlying kind of causal capacity that gives rise to it? And in the case of intervention effects, and for our discipline more generally, it's the capacity to respond and adapt to particular interventions that we're interested in. So we can think about capacities as follows. Like many of the things, as we say that we call effects, are actually incidental to the exercise of some capacity of interest. There's some sort of disposition or tendency to transform some initial state or input into a resulting output. So we can think about capacities like this. We can think about there being some sort of underlying causal capacity which takes some sort of input and generates some sort of output as a function of that output. So with regards to stalk juice, we can think about it like this. Or for example, to give an even more benign example, we can think about sorting. So the capacity to sort. So we can say we start with some input, a list of unordered numbers, and then there's some function that takes that list of unordered numbers and creates an ordered list that consists of the elements in that original list. Or with regards to an adaptation to stalk juice, we start with some input, which is exposure to stalk juice, and the output is increased performance as some function of that exposure to stalk juice. Now, I'm going to touch as well briefly on David Marr's influential tri-level framework for understanding and explaining capacities, which I also think does a nice job of providing a little bit more depth to that causal realm ontologically that we're interested in. So Marr kind of broke it down into these three levels. So we have the computational level, which is essentially just a kind of tautological statement of the capacity itself. So it's, what does the capacity do? Well, it takes some input and as a function of some input, it generates some output. So that's pretty much what we're saying with regards to the computational level. It's a statement of what the capacity does. At the algorithmic level, though, we start to ask the questions of how does it do that? How is the function implemented? What does it look like mathematically? What are the specific details of it? Is it some sort of linear function? Is it some sort of, quadratic function? Is it a step function? Or is it some sort of particular kind of algorithm? It's asking these kinds of questions that occur at the algorithmic level. And then at the physical level, this is where we start to get into the depths of how it's actually physically realized. What are the kind of structures that implement the capacity itself? So to take the sorting example, let's say, obviously, we have our capacity to sort at the functional level. We take some some input, which is an unordered list of numbers, and some sorting function that leads to an ordered list. Well, at the algorithmic level, there could actually be, again, we could abductively infer that this could happen through various different kinds of algorithms. We could use a selection sort approach or a bubble sort approach. And each of these could give rise to that particular computational level that we observe. And that could be instantiated in the physical level by a variety of different means. We could write a computer program to do it. A human brain could do it. Monkeys could do it. Or Hungarian dancers could do it. There's a reason why Hungarian dancers is there, because I've borrowed this example from work from Yves Van Rooij and José Baggio, who provide an interesting link to some YouTube videos of Hungarian dancers dancing through these different sorting algorithms. But if we think about our stalk juice example, again, we can think about performance as being a function of stalk juice, but given the magnitude of effects that we might have observed, that could be implemented in a number of ways. We could have, as I say, some sort of linear effect, which is reliant on the dose of the stalk juice, or we could have some step function that's a function of the dose of stalk juice. And this could be, again, implemented in various different ways. At the computer level, it could be implemented. So, for example, here, I've just literally created a computer simulation to simulate some data. We can instantiate it physiologically in humans or in rats. There could be, for example, human studies that have shown this effect, and there could be or shown the effect resultant from this capacity, and also rat studies, for example. Now, given this kind of tri-level framework, what I want to focus on primarily here is this algorithmic level. So thinking about what it is that specifically, what the specific mathematical structure is of the capacity that we're trying to use as an explanation here. Now, one of the problems we often have is, although the field sometimes tries to think about this in the context of things like dose responses, very rarely do we have precise theories about how they work, precise specifications of the algorithmic level that we're interested in. Instead, we're often stuck with these kind of verbal theories, which are kind of intuitive ideas about what, how, and why of a phenomena based on empirical observations and domain knowledge, and they only really express the structure of the theory in words and are limited by the imprecision of natural language. So oftentimes, if we're lucky, we might have a theory that makes a broad claim like, well, there's a dose-response relationship between stalk juice and performance, but don't specify it any further than that. And so all that leads us to think is, well, does that mean performance increases, or does it decrease as a function of stalk juice, or is there some sort of plateau function that occurs? Like, does it increase only up to a point? Without kind of more precise specification of the theory, it's very difficult to know what it entails. And a strong theory is something that deductively entails a particular set of observations. So, for example, the stronger a theory is, the more precise the deductions you can generate from it. So in our field, we are often lucky if we can come up with some sort of directional prediction or directional hypothesis derived from our theory. That is to say that instead of just saying, well, there'll be some effect that's not zero, is that we might see an effect in a particular direction. Even better, though, we might be able to come up with a prediction of an effect from our theory that is within a particular range. And the tighter and tighter that range is, the stronger the theory is itself. And the more risky the theory is, the easier it is to reject the theory or falsify the theory if we put it to a strong test. Our theory might also make specific predictions about what the functional form looks like of the capacity that we're interested in. Now, when it comes to evaluating strong theories, it's only really possible to determine how strong a theory is in the context of general background knowledge about the effects that we're trying to explain with the theory. And so Paul Meehl came up with this nice idea of what he called the Spielraum, which is essentially what we might expect the range of effects that we would observe would be given just background knowledge alone. So if we didn't have the theory to make specific predictions, what's the range of observations we could have potentially seen? And so this is important for assessing how strong a particular theory is, how precise its predictions actually are. You need some sort of background knowledge to be able to do that. So let me give you an example for this. So let's say I tell you that I'm a pretty good darts player, and I take a dart and I throw it at the board and I hit the 11. And you think to yourself, well, okay, so let's say to start off with, I think that background knowledge is James isn't such a crappy darts player that he's not going to be able to hit the board. So the fact that you said you're a good darts player, you threw it and hit the board, and you hit the 11, okay, but that's not particularly impressive. It's not particularly strong evidence to corroborate your claim. Because, I expected you to hit the board, and there's plenty of places you could have hit the board. But what if I threw it and I hit the triple 20? Well, I just told you that I'm a good darts player. I didn't tell you specifically I'm going to hit the triple 20. Now, you might assume that that's entailed by it, but given how vague my specific theory actually is regarding my ability, it's difficult to know one way or another. And again, I could have just hit that by fluke. You never know. But what if I did tell you I'm a good darts player and I'm going to throw this dart and I'm going to aim for the triple 20 and I hit the triple 20? Well, now you might start to be a bit more impressed because my theory made a particular prediction that's only a very small range of the possible range of results that I could have got given just background knowledge. But let's say now I take 5 darts and I tell you I'm going to aim for the triple 20 and I throw one dart and I hit it, I throw another dart and I hit it, I throw another dart and I just miss and get triple 1, I throw another and I hit triple 20 and I throw one more and I just miss it again and I get the 20. Now, there's a specific reason why I've given you 5 darts there as an example. I appreciate you normally throw 3, but you'd be pretty impressed, even though I didn't hit it 5 out of 5, 3 out of 5 after making such a specific prediction, and having my the 2 shots that missed be in pretty close proximity, would be pretty strong evidence for you regarding the corroboration of my particular theory. So I want you to bear that in mind as we move into the next stage, which is going through these specific examples of our recent work and how strong theory has been really valuable for helping direct that. So let's go back to this example. And as I say, oftentimes we start with data and we use that data to draw generalizations about phenomena and events that we're interested in trying to explain. So, in our case, we started off with general questions about, well, how large are the effects of resistance training? And so we've done plenty of previous research doing large-scale meta-analyses, taking studies which have made observations and using those data to conduct meta-analyses to draw generalized inductive inferences about the general magnitude and also the range of effects that we see in resistance training interventions. So with regards to strength, we see an overall kind of average effect of about 0.87 standardized mean difference, but we see this kind of broad range of effects. But in general, across a range of different kinds of resistance training interventions, we generally see these positive effects on strength and also on hypertrophy as well, with again an overall estimate of 0.34 there. So we've got this general kind of fairly probable effect that we're interested in. And so what we might now start to do is, again, engage in a little bit more induction, but also start to engage in abduction to try and come up with, well, what is it that the function could look like that leads to that general kind of effect that we see. And so, again, we've done the same here, where we've worked with large-scale studies and we have tried to derive what might the functional form be for the capacity that leads to adaptation to resistance training of the sorts of magnitudes that we see. And so what we've found is inductively, through some model fitting, we've generally kind of abductively inferred that there is this linear logarithmic adaptation to resistance training over time. So this is data from a large-scale study we've conducted of 15,000 or so participants over almost 7 years, and we tend to see that there's this initial increase in strength of considerable magnitude, and then we start to see it plateau off. And that initial kind of increase in magnitude is relatively similar to the increase in magnitude that we see in the meta-analyses. And in fact, if we go back and fit these models to the meta-analysis data as well, given that those studies in the meta-analysis were from a range of different durations of study, we also see that for both strength and hypertrophy, this linear logarithmic functional form of adaptation is still a pretty good fit for the data as well. So, using a process of kind of inductive and abductive inference, we've come up with a possible theory now that adaptation over time to resistance training in terms of both strength and hypertrophy is linear logarithmic in form. Okay, we now have this specific theory, and in fact, given that we've also got estimates of the magnitude of these effects as well, we can start to plug in some specific numbers to make specific predictions from this. So we can take our theory back out to the empirical world and we can instantiate it as a particular model and make deductive predictions from it. So we ask this question: what does the theory of linear logarithmic adaptation predict? Well, if we start with strength, we can say, well, given this model, what does it predict will happen at 12 weeks or 24 weeks or 36 weeks? And we can ask the same for hypertrophy. What happens at 12, 24, 36 weeks, or any point on there that you're interested in. So we can make very specific predictions about the magnitudes of effect that we might see. Now, we can use this then, given we've now got a model, to start to design studies and come up with operationalizations to go about actually trying to make observations and test our theory's predictions. So, we can use this to help design the studies to make sure that they are severe tests of it. So let's say, for example, we take hypertrophy as an outcome, as we recently did in a large-scale multi-site randomized controlled trial that we did. Well, we can make these particular predictions, but let's say, for example, in our study, we were interested in looking at comparisons of two interventions with on muscular hypertrophy in trained participants. Now, we were interested in looking at participants with at least 6 months training experience. And from this model, we're able to predict what the over a 12-week intervention, what we would expect the magnitude of effect to be for hypertrophy from just general resistance training interventions for people with a minimum of 6 months experience. And we can see that the difference, for example, from between 24 weeks and 36 weeks ends up being about a 0.05 standardized mean effect, which is pretty small, just to clarify. Now, because we were interested in particular intervention comparisons, even though this theory isn't necessarily about comparative interventions, it does logically entail particular predictions regarding comparisons of interventions. Because if our main effect predicted is 0.05, well, given that we know that resistance training interventions, generally speaking, are produce positive outcomes for both strength and hypertrophy, what this means is that any interaction effect or difference between differences has to be constrained. And so we think it's reasonable to then say, well, the theory itself constrains the possible interaction effect to be about half at most of the main effect of time from resistance training. And so we estimate that there's going to be about a 0.025 difference between the two interventions. We can then use this to engage in using our model again as well to conduct simulations to say, well, how many participants would we need to be able to detect a difference between interventions of at least 0.025? Well, as you can see here on the x-axis, we've got total number of participants per site, and we had 15 sites in our study. And as you can see, this kind of sets up for the problems that we'll have, we'll touch on at the end of the presentation, is even with 100 participants per site, and so over 1,500 participants, and even with multiple measurements at each time point, we've still got very low statistical power to be able to detect an effect of that magnitude. Now, if we looked, for instance, of saying, well, our theory predicts very small effects, and actually those small effects are probably too small to care about practically speaking, then instead we can use it to design our study, even using our theory to make those predictions, to then also test against some practical outcomes. So, for example, a smallest effect size of interest of 0.1 there. So, having a strong theory allows us to design and prepare a strong study to be a severe test of it. So then we can go on out and conduct our study and make our observations and generate our data, and we can conduct our test of our theory. And so, as I said, our theory predicted essentially no difference between the interventions, which is generally what we found between full range of motion and length and partial range of motion for hypertrophy, which we compared here. And similarly, we found very little difference between the interventions with regards to strength outcomes as well. But I want to come back now to this concept of the Spielraum and the predictions our theory made. And I'm going to focus on the main effects of time here because, as I said, imagine I threw 5 darts and 3 hit the place I was predicting and 2 got pretty close to it. That is essentially what happened in our study. So we had 2 outcomes for hypertrophy, 3 outcomes for strength. And what I've done here is I've plotted for each outcome the Spielraum as being the 95% prediction interval, so the range over which 95% of effects would lay in that large-scale meta-analytic data set for both hypertrophy and for strength. On the grey bar here, you've got the specific theory prediction made from our theory and our model for both strength and hypertrophy, and then you have the specific estimates for the main effect of time from our data that we've collected for this study for both hypertrophy and strength. And as you can see, 3 out of 5 of those estimates were within, or the interval estimates of them overlapped the theory predicted estimate, and only 2 of them missed, but compared to the Spielraum were very close. And using Paul Mills' corroboration index, which ranges from 0 to 1, you can see that with 1 being strong corroboration, there's very strong corroboration for our general theory of a linear logarithmic adaptation here. Okay, so theories have been very valuable then, I think, for helping guide the research that we do. And so I'm going to briefly now touch on why I think they're valuable for informing practice as well. Now, when it comes to practice, we're generally trying to make generalizable inferences that we can then bring to bear out on the real world with what we're doing. Now, typically the approach our field takes is to take a particular population to study, and that, when I talk about population, that includes the participants, the setting, the intervention, the outcome, operationalizations, etc. Take a sample from that population, typically a small sample in our field, and then to draw some sort of inductive inference to that population regarding the particular effect that we're interested in. And so often, unless we make pretty strong assumptions, the effects are limited to the particular population sampled. This has been kind of referred to as the generalizability crisis, in that we try to make overly general claims when we should probably be limiting our claims following this particular form. But when we have a theory, we can instead make deductive inferences about what should happen for a given population in terms of the effects, and then what that means in terms of observations for a particular sample. Now, our theory can have narrow boundaries, as we've shown here, or, as our theory that we've presented, it can have particularly broad boundaries. So our theory generally refers to resistance training interventions in general. And so what I think it implies is that there are broad inferences that we can make that can help inform the practice that you engage in. So from a practical perspective, it means that if you have a well-corroborated theory, you can use it to make predictions about what should happen in the population and the particular samples and individuals that you work with. So, to come back to this again, what it does is it means that once we have a good causal explanation for things, we can make specific predictions or deductions about the actual events and phenomena and effects we're interested in, and the specific then things that will occur in the empirical realm. So, in terms of practical recommendations from our work, we start with this particular theory then. Adaptation to resistance training is linear logarithmic in form over time, with rough 12-week effects of 0.32 for hypertrophy and 0.79 for strength, generally speaking across typical resistance training prescriptions. And what the implications for practice then are that contrasts between different specific prescriptions have to be smaller than the general effects over time, and given the linear logarithmic growth function over time, rapidly become too small to really care about. And so from a practical perspective, it really means that most interventions, assuming they're not ridiculous, are going to produce similar effects. And so prescription instead can be based on preferences, injury status, equipment, and time availability, and so on. Okay, I'm very quickly running short of time here, so I'm going to very quickly, rapidly run through what I think are some hard truths this implies for exercise science. So, as I've highlighted, I think what this implies is, and even without the theory, just the empirical data show this, that effects are generally pretty small. You see I've run out of time already there. Only got a couple of slides left, so. It means that the effects are pretty damn small, and given that we're particularly interested in intervention contrasts, particularly our well-corroborated theory really does predict that they should be very small. And what it means then is that the typical studies in our field are woefully underpowered to provide any kind of strong test. And so it means that currently it's difficult to use those studies as tests of theory. And so really what it means is that most of these studies are not really contributing much in the way of strong inductive inferences in the first place, but also are unable to provide strong tests of the deductive inferences of any kind of theory that we might have. But some people do still argue that these effects are important, and so if we think that these theory predicted effects are important to detect, then maybe there's some things that we should be doing instead. So, as I've highlighted, perhaps instead of seeking for differences, we should perhaps start testing for equivalence. The effects are so small that, practically speaking, it means if we think they're important, we have to do large-scale multi-site or group collaborations, or start to more creatively leverage large observational data sets. So it makes, as I say, I'm a bit thrown here because I've ran out of time and it's thrown me, so apologies for waffling now for those listening to the recording. Anyway, I think one of the problems is that given that we've got such small effects to detect, we should maybe either think about, testing for equivalence rather than intervention differences. Maybe we should spend more time on building specific theories that lead to particular predictions that we can then go out and test. And as I say, if those are small effects, we should start to think of creative ways to leverage large observational data sets and utilise causal inferences approaches for them, or to, as we've done, engage in large-scale multi-site and group collaborations to try and boost the sample size to provide more severe tests of the small effects that we think happen. Or if people continue with the current approach, then maybe what we really need to do is just be more epistemically modest and not make any claims really from the kinds of studies that we do, and instead wait for sufficient evidence to accumulate so that we can engage in robust evidence synthesis to test some of the theories that we may have. Okay, so just to wrap up then, as I say, I personally think that understanding philosophy of science and thinking about where you situate yourself with regards to that can really help in directing the way we engage and conduct our science. Apologies if you can hear the lawnmower outside as well. And certainly from my perspective, I think that engaging with theory and model formalization has really helped me to understand what theories imply about the reality we want to explain. And having those strong theories has really meant that I've been able to conduct better studies to act as tests of those theories. And once well corroborated, I think those theories make better predictions that help inform our practice. Certainly they've influenced my practice a lot now. I stress far less about, for my own training and also for any people I provide recommendations to, about what are going to be, if they exist in reality, tiny differences between interventions. Lastly, as I said, I think going through this process of formalizing and working with strong theories really does emphasize how difficult our science can be, and that if as a field we're continuing on the current route we're continuing on, which is to just continue producing lots of data via small samples, we need to think about whether that's an appropriate route that we want to take forwards, or whether we should start to engage more with utilizing building stronger theories and then utilizing those to try and direct the work that we're doing. Apologies for the waffling at the end there, the timer going off and also the lawnmower in the background, which I'm not sure you can or can't hear on the recording, went off. So I think I need to run through that slightly more quickly when it comes to it in the actual presentation, which I'm sure I will do once I'm actually up on stage talking in person. But yeah, one last thing I will leave you with is there is an incomplete draft of a second chapter for the Stork textbook that I started writing on theory testing and building. It's going to remain incomplete and it's not going to make its way into the textbook chapter, at least not during this version, because it grew into a mammoth 25,000 word monster of a thing, and it's not even 2/3 completed yet. So but if you are interested, then there is still a lot of content there. Please do feel free to have a look and see some of the wider thinking that I've been having around this topic as well. Anyway, it's always weird sitting here and talking to a computer on your own. I'm also impressed that Kiki, my cat, didn't come in and interrupt whilst I was talking, because she normally wonders who I'm talking to when I'm doing this sort of thing. But yeah, hopefully that will be of interest to people, and yeah, looking forward to hopefully finding some time, maybe over the next 6 to 12 months, to sit down and put pen to paper and start to put this into more of a structured paper.